So in my last complex numbers video, I left you off with a cliffhanger. How do we multiply complex numbers? We discovered in the video that graphing complex numbers is as simple as converting them to regular rectangular coordinates and then plotting them on a coordinate plane, as we are used to. Adding them and subtracting them is just a matter of combining like terms. But how do we multiply this? If you watched my multiplying polynomials video already, then you probably know what's coming. But I want to start this video off by talking about powers of I. So what I'm going to solve for is I'm going to solve for I to the 0, I to the 1, I squared, I to the third, I to the fourth. Okay? I'm going to stop there and you'll see why. We're going to think back to our properties of exponents to help us solve these. Well, I know that anything to the power of 0, so long as it's not 0, is equal to 1. So I to the power of 0 is 1. That property still holds. I also know that anything to the power of 1 is just itself. So there we go. Now I squared. Well, we have to think about this as being in terms of I times I. Do we have a rule for this? And the answer is we do. We have to think about the definition of a complex number as being the square root of -1. This is how we define it to be. This is how this was discovered, was by taking the square root of -1. Well, if I just go ahead and square both sides, this cancels with this, and I get -1 is equal to I squared. So this just leaves me with -1. Okay, let me go ahead and tidy that up for a second. So I know that I squared is equal to -1. So what about I cubed? I cubed, well, we could look at that as I squared times I to the first. And we can do this because we're just using properties of exponents. 3 is equal to 2 plus 1, and they have the same base, so we're good. And that we do this so we can draw on our previous knowledge. I squared is equal to -1, and I to the first was equal to I, which this just leaves us with a -I. Notice I'm not getting anything too complicated in here. I'm not getting like a 5i or a 7i plus 6 or anything like that. Just getting patterns of 1s and i's and negatives. Okay, so let's deal with I to the fourth. So we could break this into I to the third times I to the first, or we could do I squared times I squared. I'm going to choose I squared times I squared because it's a property that we're going to use most often. This idea that I squared is equal to -1. Get used to that one the most. And so I squared times I squared, well, that's just -1 times -1, which -1 times -1 is +1, which means we've looped back around to I to the 0. So we have a repeated pattern that we might have established. Let's check one more example. I to the fifth. That'd be I cubed times I squared. I know that I cubed is -I, and I know that I squared is -1. Well, negative times a negative is a positive, and so we get I times 1 is just I. That's the next pattern in the sequence. So now we can use this pattern. Say we wanted to solve for I to the 54th. Well, let's take a notice. First of all, 54 is an even number, so the answer is either going to be -1 or 1. And if we notice this, I to the 0 and I to the fourth, the powers were multiples of 4. So if it's a multiple of 4, we can conclude that the final answer will be 1. However, if it's 2 more or less than a multiple of 4, like 2 is, if it's an even number that's not a multiple of 4, so 2, 6, 10, so forth and so on, then the answer will be -1. So it stands to reason. Let's take 54 and let's divide by 4. So 4 goes into 5 one time, minus 4, so that's 1. And then we drop the 4, and then 4 goes into 14 3 times, so 3 times 4 is 12, and I'm left with a remainder of 2. Okay? So this remainder here indicates that it is not a multiple of 4, which means this would be the same thing if we reduce it down to I squared, which is -1. Now, if you wanted to write all those properties of I to the fourth, I to the fourth, I to the fourth, because I to the fourth is just 1, you'd have to write out 13 groups of them plus an additional I squared, which gives you the -1. So that's a handy property I like to point out. Now back to the main problem. How do we multiply complex numbers together? Well, this is where I'm going to relate directly back to my multiplying polynomials video. I'm going to look at setting up an area table. So I've got 3 minus, and let's write this as 1i, and then I'll set up my table. And then I've got 2 plus 6i here. Okay, and we know what to do here. 2 times 3 is 6. 2 times -1 is -2, and then again, we treat the I kind of like it's a variable, but we won't. It's not a variable. 6 times 3 is 18, and we still got the I. Then we get 6 times -1 is -6. Then we get I times I is I squared. Now, in the area table, when it was polynomials, the like terms fall in the diagonal. And that's true here. So 18 minus 2i, this is 16i. So we've got our imaginary part. But this is what's throwing me off here, this I squared. Well, this is why I like to go over the powers. And I squared is the big one that you really need to hold on to with all your might, because this is the one that comes up most in calculations. Okay, so this would be I squared would be -1, but what that ultimately leaves us here is -6 times -1, which is a +6. And now if we look at what we have, we also now have like terms in this diagonal as well, because we've gotten rid of the complex part. And so we get 6 plus 6 is 12. And so our final answer is 12 plus 16i. So that goes to show you that at the end of the day, we are looking at just doing what we did with multiplying multiplying polynomials. Pardon me, I lost my train of thought there. What if I say I wanted to do this? Well, this would be 3 minus I times 3 minus I times 3 minus I. This is where it is handy to know the double distribution idea and not just the area model for multiplying these kinds of things together, because we would have to create what is effectively a cube model to multiply this out, and I don't think anybody wants to be drawing and subdividing a cube into little parts. It would get confusing. But what you can do is you can do the area model twice in this. If you want to see that for a future video, please let me know and I can do that. And then another cliffhanger I will leave you off with is what do we do, pardon me, when we have that? So go ahead, if you like this video, give it a like, subscribe, and a comment down below, and I will see you in the next video. Thanks for watching.